Thus far, we've been talking about contact-based temperature sensors, where we actually need to touch the temperature sensor on the material that we're trying to measure. But we also have non-contact temperature sensors, and there's lots of advantages and reasons why we might want a non-contact temperature sensor. It might be that we're actually just trying to locate the source of particular heat. We might have a circuit board or a motor or something like that. We're trying to work out where the heat is actually coming from, rather than just how hot the whole thing is. We might be trying to work out, when we're doing thermal insulation, where heat's escaping from or where coolness is coming in. We might be trying to measure something really, really hot in a cost-effective way, and it might be too hot for some of our other temperature sensor types. And we might just want to measure temperature at lots of different locations and not be constrained to where the sensor is actually mounted, but lots of different locations. One place that I use these all the time is when I'm cooking pizzas. I've got an outdoor pizza oven, and we cook pizzas at about 400 degrees Celsius. At 400 degrees Celsius, the pizza cooks in under 2 minutes. And that it makes the crust rise up really nicely. The way I measure the temperature in here is not by putting my finger in there and working out how hot it is. Otherwise, I'd have a burnt finger really quickly, and second-degree burns are no good. I use a non-contact temperature sensor, and it basically tells me straight away how hot it is. Is it 200 degrees where it needs a bit more heat, or is it 450 degrees where I need to start cooling it down a bit? The standard temperature sensors we use for this sort of application, and the ones previously mentioned, are these IR-based thermometers. Now, basically how these work, they're detecting the amount of thermal radiation or the infrared light emitted by an object. Earlier on, we talked about the Stefan-Boltzmann law, where the hotter something gets, the more infrared light that will be emitted by that particular object. And so that's what we're relying on for these sort of measurements. Now, we see this infrared light is outside the measurement spectrum what our eyes can sense. So this infrared light is invisible to our eyes, but we can actually measure it with our different measurement sensors. Now, I've already said the amount of infrared light an object emits increases with temperature, but there's another factor as well, and that factor relates to the actual material that we're dealing with. And this factor is the emissivity of the material. Materials have different emissivity factors. And basically, it's a factor of how well a particular material can emit energy as infrared radiation. It's calculated as on a range of 0 to 1 in a ratio of what it would be compared to, for a particular material, to a black body representation of that material at the same temperature. So if it's 0, it's going to be a perfect reflector. And if it's 1, it's basically going to reflect nothing. Now, we see a table here of a whole lot of different materials, from things like a polished aluminium surface, where they're actually quite good reflectors. And we know that. We look at some polished aluminium and we can see ourselves in it, for example. We don't just see ourselves, though. Well, our eyes just see ourselves. But the infrared radiation that's emitted from other objects is actually reflected by that piece of aluminium that's quite shiny. And we can see that, or at least our temperature sensors that are measuring infrared light can see that as well. Now, many IR thermometers have a default value of 0.95 because a lot of materials are around this 0.95 range. And it really depends on how accurate our infrared thermometer needs to be. Some more expensive infrared thermometers, like some of the Fluke ones, might have a high, medium, and low setting for measuring the amount of infrared radiation for materials with different emissivities. So if our emissivity is quite low, we're getting a lot of reflection. And in many cases, we might be, for example, in the picture above, we might be measuring the temperature of that reflection rather than the temperature of the actual material itself. You see there's a polished block of metal there. One side of it you see is painted black, which is a bit like that ideal black body radiator there. And that, if we measure that part of it, it's telling us what the temperature is of that particular device or that particular block of metal. What we see next to it, it's quite shiny. And we see, if we look at the infrared view of that using the thermal camera, we see we're actually measuring the temperature not of that cube, the cube's all at the same temperature, but we're measuring the temperature in the infrared spectrum of the person's hand, which is sitting next to that cube because it's being reflected and then reflected into the detector that we're using for our detection. So that's something to keep in mind. And so one thing that people can do if they're trying to measure something that's quite shiny or reflective is you can put some black electrical tape over it, something that's not so shiny, and the emissivity will be lower than what it would have been previously. and it will heat up to about the same temperature as what we're measuring, and we can measure that black electrical tape or material rather than the shiny surface that was reflecting off something else. Now, how do these actually work? Well, essentially, these infrared thermometers use a lens, and that lens focuses light onto what we call a thermopile. The thermopile is essentially a whole collection of little thermocouples that we join together, and we use that to measure heat. So if we have more infrared light that is reflected onto our thermopile, we have more heat, and we're going to heat up that thermopile by a larger amount. One other thing to keep in mind is these will often have a laser on them, and some people are tricked into thinking we're measuring the temperature of that tiny little laser dot. We're not. The laser is actually just there for aiming, so you know roundabout's the center of the circle that we're looking at measuring. The further we get away from the thing we're trying to measure, the larger the dot is. So at about 12 inches, we've got about an inch of the size of the dot we're trying to measure. We measure further away, we increase the size of that area to, if we measure too far away, well, we're actually not getting enough thermal radiation to register properly on our sensor anymore. There's lots of applications for these. So around all the COVID things, lots of people went for these non-contact infrared thermometers. So they didn't need to put something in someone's mouth and swap thermometers around. And it's quite a quick way of taking a measurement. Depending on exactly how it was measured, you may have had some experience where this hasn't always worked so well. If rather than measuring on your head, it's measured part of your hair or something like that. Sometimes the reliability of these for those fine-grained measurements isn't always there. We can use them for measuring, for example, how hot a motor is or something like that, and working out whether it's under load, whether it needs to be serviced or something. I've mentioned the pizza oven example, which is what I use it for almost every week. And we can use it on something like a circuit board to work out, is it heating up too much? Or are we running too much current through it? One of the nice things about this is it's portable. We can take it with us, we can do measurements, and then we can put it away, and we can measure a whole lot of different points, not just a single point where our thermistor or our IC temperature sensor is mounted. That brings us to something that is a little bit more advanced than that, which is using thermal cameras. So rather than just trying to detect one little point, we want a whole array of points. And across that array of points, we want to develop a thermal image of what it actually looks like. And so we use a device called a microblotometer. Here's a picture of one here. And they typically have fairly low resolutions, although some higher resolution ones are coming out. So it might be something in the order of 320 by 240 pixels. And each one of those pixels will be able to measure the temperature of that particular point. Once again, using infrared, just like we did with our previous approach. Here we've got one device which is a whole array of those infrared sensors. Now there's a bunch of different applications for these thermal visioning cameras, from detecting where people are when people are trying to run away from police or something like that. We can see thermally people or animals standing out quite clearly against other surroundings. And it essentially can allow us to see in the dark as well, because we can see where those people are. We can see through some objects where thermal energy can transfer well through. So you can see the picture there of the guys with a plastic bag over his head. We can see him underneath that. Firemen use these to work out the source of where fires are and where the fire's burning. They can use them to look at a door if it's going to be too hot before they actually touch the door and try and open it up, and there might be a fire on the other side of it. We can use them for buildings and looking at buildings and looking at where heat's escaping from the building or where coolness is coming into the building. And we can use them, I use them sometimes for circuit boards, where I'm looking at where, if there's too much current going through a board, where is it failing? There might be a track that's shorting out or something like that, and that track will start heating up like a little fuse. Or looking at motors and working out where the hottest parts are and why they're heating up. And in that case, they might need a service. Now, there's different color maps that are used for this sort of thermography. The standard ones we call the hot iron palette, which is the one down here where we're looking at the palette where we're looking at oranges through to blacks. But typically when we're trying to find people or something like that, we use the white hot palette where we see people or animals standing out against the background there. So these are used in lots of different applications and are quite powerful as a non-contact way for localizing the source of some heat.